What if I told you that you can describe every location in the universe using just three numbers, but mathematicians can add a fourth, and that changes everything? Not a fourth direction you can point toward, not some magical portal, and not the science fiction version where people suddenly walk through walls. A genuine fourth spatial dimension is a mathematical concept that follows the same rules we already use for the dimensions around us. The strange part is that your brain has almost no way to actually visualize it. So let's start with something we can understand. Imagine a creature that lives on a perfectly flat sheet of paper. For this creature, the entire universe is a 2D plane. It can move left and right, forward and backward, but there is no concept of up. If you lifted your finger above its world, you could see something the creature could never see. The entire 2D world from a direction that doesn't exist inside it. Now imagine placing a circle directly on that creature's world. To the creature, the circle is just a strange shape, but if you moved a 3D sphere through the 2D plane, the creature wouldn't see the sphere itself. It would see a point appear, grow into a larger circle, shrink again, and then disappear. One 3D object would look like a sequence of changing 2D objects, and this is where the idea of higher dimensions becomes genuinely strange. Now replace the 2D creature with us. We live in three spatial dimensions: left, right, forward, backward, and up, down. We can move in all three. But if a fourth spatial direction existed, it would be a direction perpendicular to all three of these at once. And that's the part our brains struggle with. You can't simply point toward it because every direction you know is already built from the three spatial dimensions around you. Mathematically, however, there's nothing mysterious about adding another coordinate. In one dimension, you need one number to locate a point. On a flat 2D surface, you need 2. In ordinary 3D space, you need 3. A point in a four-dimensional spatial space would require 4 independent coordinates. And once you accept that, you can build four-dimensional versions of objects we already know. A square is a 2D object. Move it into a new perpendicular direction and you get a cube. Then take that cube and extend it into another independent spatial direction, and mathematically you get a four-dimensional cube, better known as a tesseract. A tesseract isn't just a weird drawing you see on the internet. It is a perfectly well-defined mathematical object. It has 16 vertices, 32 edges, 24 square faces, and 8 cubic cells. But you've probably seen a tesseract drawn as a smaller cube inside a larger cube with lines connecting their corners. That drawing is not what a tesseract literally looks like. It's a projection of a four-dimensional object into our three-dimensional world, just like a shadow is a projection of a 3D object onto a 2D surface. Think about your own shadow. If you hold a cube in front of a light, its shadow can appear as a complicated 2D shape, but nobody would confuse the shadow with the actual cube. The same basic idea allows mathematicians to represent a 4D object using a 3D projection. We can't directly see the fourth spatial direction, but we can calculate what a four-dimensional object would look like when projected into 3 dimensions. And there's an even better way to understand this. Imagine a 3D sphere passing through a 2D world. The 2D inhabitants never see the sphere. They only see its cross-section. First, nothing. Then a tiny circle appears. The circle grows larger as the sphere moves deeper through their plane. Eventually, it reaches its maximum size. Then it shrinks and disappears. From their perspective, the object has appeared from nowhere, changed size, and vanished. Now reverse the situation. If a four-dimensional object passed through our three-dimensional space, we wouldn't see the entire object. We would see changing three-dimensional cross-sections of it. Something could appear, grow, change shape, shrink, and disappear without ever moving through our three familiar directions in the way we're used to. This isn't a claim that such objects actually exist around us. It's a geometric consequence of imagining an additional spatial dimension. And this gives us one of the most famous thought experiments in higher dimensional geometry. Imagine a four-dimensional being looking at our world. If such a being could somehow interact with our 3D space from a fourth spatial direction, it could potentially see the inside of a closed three-dimensional object without opening it. Why? Because just as you can look down on a 2D drawing and see its entire interior from the third dimension, a hypothetical fourth-dimensional observer could have a direction of access unavailable to us. A locked box wouldn't necessarily be a complete barrier from that perspective. The walls that completely surround something in 3D might not completely surround it in 4D, and this is where the idea starts sounding like magic, but the geometry itself isn't magic. It's the same relationship we already established between 2D and 3D. A 2D creature might think a sealed circle completely encloses its interior, but you, as a 3D observer, can simply lift an object out of the plane without crossing the circle's boundary. From the creature's perspective, the object has somehow escaped a sealed prison. From ours, nothing supernatural happened, we simply used a direction the creature couldn't access. The same logic works one dimension higher, but there is an enormous catch. We have no experimental evidence that there is a fourth spatial direction that we can freely move through. In everyday physics, space is described using three spatial dimensions. When physicists talk about four-dimensional spacetime, they are usually talking about 3 dimensions of space plus 1 dimension of time, and those are not the same thing as a fourth spatial dimension. This distinction matters because you've probably heard someone say, time is the fourth dimension. In physics, that is a useful way of describing spacetime, but time behaves differently from the 3 spatial coordinates. Relativity combines space and time into a 4-dimensional spacetime, and different observers can disagree about how space and time are divided while agreeing on the underlying spacetime events. So when this video says fourth dimension, we're mainly talking about a hypothetical fourth spatial dimension, not simply time, and that brings us to one of the strangest questions. If a fourth spatial dimension is mathematically possible, why don't we see it? The honest answer is that we don't know that such a dimension exists in physical reality. Mathematics allows us to construct spaces with 4, 5, 10, or even more dimensions, but mathematical possibility is not the same thing as physical existence. Some theories of physics have explored extra spatial dimensions. For example, certain models associated with string theory involve additional spatial dimensions, while some theories propose that extra dimensions could be hidden or compactified at scales far smaller than we can directly observe. But these are theoretical possibilities, not established discoveries of a hidden fourth spatial direction. And that's an important line to draw. A tesseract is real as a mathematical object. Four-dimensional geometry is real as a mathematical framework. Four-dimensional spacetime is part of modern physics, but a macroscopic fourth spatial dimension that humans could physically enter, walk through, or use as a shortcut has not been demonstrated. Yet there's another reason this concept is so difficult to imagine. Our brains evolved to navigate a three-dimensional environment. You can easily imagine moving forward, sideways, or upward because your entire experience is built around those directions. But trying to visualize a direction perpendicular to all three is like asking the 2D creature to imagine up. It can understand the mathematics, but it can't directly experience the direction. That's why scientists and mathematicians rely heavily on analogies, equations, cross-sections, and projections. We don't need to literally see a fourth dimension to reason about one. In fact, humans routinely work with mathematical spaces that cannot be visualized directly. A four-dimensional object can be described by coordinates, its properties can be calculated, and its projections can be represented on a screen. The same way a photograph gives you a 2D representation of a 3D scene, a visualization can give you a lower dimensional representation of a higher dimensional object, and there is one final twist. If you were somehow a creature living in 4 spatial dimensions, our world might seem incredibly limited. Imagine looking at a 2D world from above. You could see an entire maze at once. You could reach into enclosed regions without crossing their boundaries. You could observe shapes from an angle that its inhabitants couldn't even define. Now imagine what a 4-dimensional observer could theoretically see about our 3D world. Our most secure rooms might not look so secure. Objects we consider completely enclosed might be open from another direction. And a 3D object moving through a 4D space could produce bizarre changes in the 3D cross-section we observe. But remember, this is geometry, not evidence that 4-dimensional beings are secretly watching us. That's where science and imagination have to be separated. We can use mathematics to explore what a fourth spatial dimension would imply without pretending we've discovered one, and maybe that's the most fascinating part of the entire idea. The fourth dimension doesn't need to be a portal, a hidden universe, or an alien world to be mind-bending. It shows us something much simpler. Reality can contain structures that our senses aren't built to visualize. A 2D creature could never look up no matter how hard it tried. We can look in every direction our three-dimensional world allows, but if another spatial direction existed beyond them, we might be in exactly the same position. We wouldn't necessarily know what we were missing. So, is the fourth dimension real? If you mean four-dimensional spacetime, then yes, modern physics describes our universe using 3 spatial dimensions plus time. If you mean a fourth spatial dimension like the one in a tesseract, Mathematics can describe it perfectly, and physics has explored theories involving extra spatial dimensions, but we currently have no confirmed evidence that humans inhabit a directly accessible fourth spatial direction, and perhaps that's the strangest lesson. The universe doesn't have to be impossible for us to understand it. Sometimes we can understand the rules of something long before our brains can actually picture what it means. We can't see the fourth spatial dimension, but we can describe it, calculate it, project it, and explore its consequences. And if one day physics proves that an extra spatial dimension really exists, the most shocking part may not be that we discovered a new direction. It may be realizing that the universe has always been bigger than the three-dimensional picture our brains were capable of drawing.